All right, so again, the plan for today is to talk more about multi-way cut and randomized rounding. So remember that we discussed the problem of K multi-way cut given an undirected graph G and K terminals S1 to Sk. You have to remove the set of edges, a set of edges of minimum cost that separate all the terminals from each other. For k equals 2, this is just ST min cut, polynomial time solvable. For k greater than or equal to 3, this problem is NP hard. The first thing we discussed in the last lecture is there's a fairly simple heuristic called the Isolating Cut Heuristic. It's a simple algorithm which just basically runs a bunch of min cuts, and that gives a 2 approximation, or a 2 times 1 minus 1 over k approximation. Now, where we went from there was to actually now think about an LP rounding scheme. So, inspired by min cut, we defined an LP rounding scheme, LP for multi-way cut, which simply says that you have distance functions, the shortest path distance function from each of the terminals. So you have a di for each from each source. So di of Si is 0. Di satisfies all the distance conditions. Di of Sj is greater than 1. So the distance between the terminals has to be more than 1. And you want to choose xe's, which is sort of the cost of the, whether you're going to cut that edge or not, right? And that's what it would be in the IP. And in the LP, it's just greater than or equal to 0. This is a relaxation. Then doing a randomized rounding with this scheme, what we could prove is that by doing a randomized rounding, the probability that an edge is cut is twice XUV, is twice the LP value of that of the edge. And just recall that the way that we define our clusters was we would pick an R at random from 0, 1, and we would define script Si to be the cluster that contains Si, this terminal Si to be all the vertices within distance R. And we argued that, for this case, the right thing was to pick it between 0 and a half, and we would get a 2 approximation. So that, when we put it all together, again gave a 2 times 1 minus 1 over k approximation. And you might think, well, that's not much better than what we got with the greedy scheme. And then we said, and also we showed that the integrality gap of the LP was actually 2 times 1 minus 1 over k. It's actually exactly that, because we were able to achieve this approximation factor. And a simple example was the star. So in the star, the LP would basically put a XE to be half on all the edges, and all the pairwise distances between the leaves would become 1. So then there's this significant result of Calinescu-Karloff and Rabani called the Ckr Relaxation. And that is what I'm going to discuss now. So with that, the topic for today is the Ckr relaxation and rounding. Yeah.
Should I be scribing?
You scribed the previous lecture, right?
Yeah.
Then it's fine. You don't need to. But send me the notes as soon as you can. I will append.
I will finish the notes by Saturday, Sunday.
Sure, that's fine. That's fine. So the Ckr relaxation and rounding for multi-way cut. And hopefully, if we have time, I might also go into a problem called multi-cut. Okay. So what was the idea? So the idea was to say, let us think of the integral or the discrete problem in terms of a metric. Okay, so what's the idea? The idea was to say that we have variables. We have variables d, u, v, which is going to be equal to dvu, right? So symmetric, which is the distance from u to v. And we're going to minimize the sum over all edges of, the cost of that edge times the distance of the vertices in that edge. Remember, the distance is for all pairs of vertices. This is for all pairs, not just for edges. Right? So this distance we define for all pairs. And then what we can do is we can just write down the metric conditions. Right? So for all so for all u comma v, the distance of uv is equal to the distance of vu. For all uv, the distance of u to u is 0. The distance of u to v is greater than or equal to 0. And for all uvw, this is triangle inequality. And then we said that for all I not equal to j, we want the distance from si and sj to be equal to 1. So any function that satisfies these conditions is called a semi-metric. I mean, it depends on what you look at. Some people call it a semi-metric. Some people call it a pseudo-metric. And it's a pseudo because technically in this definition, we allow the distance between different points or different vertices to be 0. And in a metric, that's not allowed. In a metric, usually if the distance is 0, the distance of a point to itself is 0, and to any other point is always non-zero. Okay, so this is a semi-metric. Now, one thing one can see is that if we enforce the distances to be either 0 or 1, if we enforce all distances to be either 0 or 1, then we can actually get this basically just becomes the IP, or this just becomes the standard problem. So why is that? We could just say that for every time an edge is cut, you say the distance between those two endpoints is 1. And then for any edge that is not cut, think of putting a 0 over there, so that edge would not be cut. And then when you have connected components, the distance within connected components is 0, right? So essentially what this says is if you look at any setting like this, then the distances between these are 1 and the distances between these are 0. So for all vertices here, not just those with an edge, but for any pair of vertices, the distance between these is 0. For anything across the clusters, the distance is 1. I'm abusing notation a bit, but this specific metric, it can be called a cut metric. It's actually, cut metrics are only when you have two sets. So this is like some sort of k-cut metric, right? So you always have a metric with this. But this is a relaxation. So the LP is optimizing over all metrics, whereas what you want is in some sense a discrete cut metric. This LP solution is going to be something continuous. Now on top of this, we are going to add extra constraints to help us get a better solution. Partly, now I don't know how they came up with these constraints, but I'm guessing inspired by the integrality gap example. What they said is if you look at this situation, in the discrete setting, you have the condition that for all vertices u, the summation of I going from 1 to k of the distance of si to u, this is exactly k minus 1. Right? Because for every vertex, you could assume that it's going to sit in some cluster. Right? So its distance to S, the terminal in its cluster, you can basically assume, you can always assume without loss of generality that each of the clusters has a distinct terminal, because if it didn't have a terminal, then you could absorb it into some other cluster. right? You can absorb it into some other cluster and improve the objective value. So each connected component has a distinct terminal. And so the sum of distances to all the terminals should be k minus 1. So this is then gets rid of this example. Because for this middle vertex, the sum of distances was k over 2. Secondly, what we would like the metric to make the distances between vertices as large as possible, like those that are in different clusters. So we'll add an extra condition that for all vertices uv, the distance between u and v is greater than or equal to the summation of I going from 0 max of the distance of SIU minus the distance of SIV, comma 0. This is not a linear constraint, but it can be converted into one. It can be converted into linear constraints. You just create a new variable for the max, and you make that variable be more than 0 and more than this. You can always convert a max into a linear constraint. Okay? So what this does is it says that if you take any two vertices, so go back to this picture here. If you take two vertices that lie in different clusters, then this sum of all maxes becomes at least 1, right? Because essentially there exists one of these terms, which is 1, and everything else will be 0, so the distance will be at least 1. And if they're, of course, in the same cluster, then this is just a lower bound and you just get 0. So this entire LP, this is the Ckr relaxation. Any questions about this relaxation? Any questions? Yeah.
Going on with the last two constraints, I mean, I missed that. I mean, do we impose those additionally to the previous ones?
Yes,
or,
we're adding these constraints in. So if you don't have these constraints, then there's an integrality gap of 2.
I see. So this is just to like start to tighten the gap, right?
Exactly. But what we'll see is that this is going to lead to a very beautiful structure.
Okay.
But yeah, and it's a good question as to why did they put these constraints. This one, the first one I can see obviously removes the integrality gap because the star is a bad example. But the problem with the star is this middle vertex is equidistant from everyone. You don't want that.
Exactly, yeah.
This condition to me is a little bit more mysterious. But it's basically saying that, you want things to look like kind of like a cut metric, right? You want everything to be either on one side or on the other side. And this is sort of pushing things in that way, that if you have two vertices whose distances to the clusters are significantly different, then you want them to be far away.
I see.
Now, but you're going to see that this is going to lead to a very beautiful formulation of this second constraint.
So that's just SI the K terminals, right?
I'm sorry? SI to K, yes. Is that what you were asking?
Yeah. I was slightly confused by the upper limit.
Yeah. It's basically just that. Yes, exactly. Yeah.
I still didn't get why the inequality holds about the last inequality.
Hang on a second. Sorry. So
The DUV is larger than max D SIU minus D SJV. Yeah.
So you're not sure. Okay. So look at let's say the optimal clustering, or look at any discrete solution. A discrete solution is going to create these connected components with each of the SIs. Right?
Yes.
Now let's take any two vertices, U and V. And suppose they lie in different clusters. their distances to any of the other terminals are both 1. So the distance from U to S1 is 1, the distance from V to S1 is 1. So all of those are going to be 0. But the distance to S3, Si has a distance of 0 and V has a distance of 1. Okay, so again this becomes 0. But the distance of U to S4 is 1 and the distance of V to S4 is 0. So then this becomes 1 and hence DUV is more than 1, greater than equal to 1.
Oh, I see.
It's important that you put the max. If you simply summed everything up, you would just get 0.
Yeah, I see. Yeah. So it would be really simple that if U and V lie in the same component.
If U and V lie in the same component, their distances to every other terminal is the same, and therefore this just becomes 0.
Yes, I get it.
So in some sense, this constraint is valid for the integral solution. So we can go ahead and put it in because it's a linear constraint. Because we are trying to tighten the integrality gap. Okay?
Yes, okay.
Okay? All right. Any questions? Further questions? Okay, let's continue. Okay, so I want to have this picture. I want to have this back here, and really I'm going to we know that this is a metric, so I just want to keep these two constraints in front of us. Metric, and we know this is true. Okay. Now here is something that I think is really brilliant. So we're going to run this and we get some solution. Let us interpret the solution as follows. For every vertex U, consider the vector. Okay, I'm going to make a k-dimensional vector. So k is basically 1 for each terminal. I'm going to create this k-dimensional vector, which you'll see why I'm doing this. I know that, okay, so you can prove that essentially all the distances are going to be at most 1. But if you want, you can just add that as a constraint. So go ahead and add that as a constraint to the metric. Right? All the distances are at most 1. So xu is going to be 1 minus, I'm just going to write 1 minus the distance of S1 to U, 1 minus the distance of S2 to U, 1 minus the distance of S3 to U, so on and so forth. Okay. Okay, now what are some properties of this? So firstly, observe all coordinates are non-negative and at most 1. What more properties can you say based on these things? What is the vector corresponding to a terminal? What is the vector corresponding to a terminal?
So that will be 0 for 1 for exactly the SIth position and 0 for everything.
Right. So essentially, where the SI is just the ith position. This is exactly the unit vector. Where this is the ith position. So each of these are unit vectors. Okay. What is the L1 norm? What is the sum of coordinates? What is the sum of coordinates?
Is it not 1?
It's 1, exactly. So you have every vector has non-negative coordinates and has a sum of 1. This is a distribution now. So for all u, essentially xu is a vector in delta k. This is the k-dimensional simplex. So each I can interpret the solution for each u vertex. I get a vector in the k-dimensional simplex, where for the terminals, they're all are the unit vectors. And this is the convex hull of those unit vectors. So one way of thinking of this, of the solution, is if I just draw the k-dimensional simplex over here. This is the vector for each of the terminals, and for each u, I get some point inside the simplex. Okay? But what is even better is let's just say, and you can argue this based on the LP, suppose the distance between u and v was exactly this quantity. Suppose it's exactly this quantity. So observe the following. dSiu minus dSiv is exactly equal to xv ith coordinate minus xu ith coordinate, right? Because that's how I set these vectors up. Right? Now, assuming this was an equality, suppose you assume this is an equality, then you get duv, the distance between u and v, is basically equal to the sum of I going from 1 to k of the max of xvui minus xui comma 0. What is this? So I have these two distributions. I have two distributions. And I'm basically taking the difference of coordinates where v is larger than u. What is this quantity called? Any hunches? You have two distributions. You're summing over the support of the distribution. You're looking at where one distribution has more probability than the other, and you're subtracting all of those. This is a norm between distributions. What norm? This is exactly the total variation distance between the distributions. The total variation distributions is half of the one norm. So therefore, the distance between the points is basically the one norm, although technically it's a total variation. So we'll stick with total variations. The total variation is exactly this. What I've written here is exactly the total variation distance. And you can prove that the total variation distance is half the one norm. So now the nice thing is we can actually ignore the distances from our entire picture and simply think that the LP is outputting vectors over the k-dimensional simplex. It's just outputting vectors over the k-dimensional simplex, and the distance, the DUV, is just the total variation distance. Right? So this is beautiful now, because now we have a geometric interpretation to the LP's output. And now we can talk about one norms, which is much more convenient than having to deal with, arbitrary distances. And then the rounding is now going to be a lot easier to, we can now actually get a lot of information. Does this make sense? Please ask me any questions about this. This is very important that you understand this part, because this is like everything else is going to hinge upon this.
So what does TV stand for?
TV stands for total variation. You'll see this appear a lot in even like machine learning and analyses, where they'll take the total variation distance between distributions. And total variation distance is a fancy word for basically half of the one norm. And it's exactly this formula. There are other ways that it is also written. It is also written as follows. This is also written as the max over all subsets of the sum over all I in the subset of XVI minus XUI. It's also written as follows. It says that look at every possible subset of coordinates and then take the difference. And you'll see that this is maximized precisely when the subset is where XVI is greater than XUI, greater than equal to. So it's exactly, these things are equivalent. You can prove that it is half the one norm. That's a calculation that you can do. And this is the total variation distance between the distributions. So the distance that we get out of this LP comes out to be total variation. And for that, we critically need these two constraints. First constraint puts everything on the simplex. The second constraint makes it the total variation distance. And I think to some extent their intuition behind putting this constraint was to force things to look like total variation. They were probably thinking of how do we get this to be geometric? And this was a linear constraint that led to that. Any questions? Now, I did a little bit of a fudge and I said that I'm assuming the distance is going to be exactly this quantity, whereas the inequality only says this is greater than equal to. But, believe me that when the LP finishes, you can argue that these will be equivalent. Okay, so it turns out, I just want to write this out as a separate line so that we have it in front of us. The LP is equivalent to put all vertices in the K-simplex, the K-dimensional simplex. Fixing XSI to be the unit vectors, right? So we basically put all the terminals as unit vectors. And what we want to do is we want to minimize the sum over all the edges. Put all vertices U in the K-dimensional simplex as the vector XU, or the distribution. Total variation. And again, total variation is half of one norm. The total variation distance is half of the 1 norm. So the LP is equivalent to this, and now we'll just work with this formulation. Okay, now we are going to do our randomized rounding. And we're going to do a slight change to the randomized rounding. We're going to change the randomized rounding. So how are we going to change it? We'll say, so previously, remember, the randomized rounding was generating this S1, S2 up to Sk, and Si was set to, now in this case, we can use the same thing, all vertices V, such that Si minus V total variation is at most R, where R was chosen uniformly at random. Now we said 0 and half over there. Let's just do 0 and 1, and we'll see that this is good enough. Right? So this is how we chose these SIs. How it was mentioned last time was also an idea, well, can you get some improvement by observing? So for example, when you have this graph here, and let's say you generate, this is S1. And let's say S2 was generated here. There is no need to cut these edges. So when you have S1, you can actually remove S1 from the graph, and you only need to cut these edges. Right? It is an overkill to cut these extra edges. It is an overkill to cut these extra edges. And so we will use that over here. So we'll just say, we will pick R uniformly at random from 0, 1, set SIs as follows, but we're not going to cut these edges. Don't cut yet. I will just initialize x is equal to 0. And then what I'll do is in order 1 to k, cut the edges in SI set minus x, right, to x set minus SI. Sorry, you know what? I don't have enough space here. Let me rewrite this. Let me rewrite this in a better way. My apologies. I'm just going to rewrite it so that it'll be a lot more clearer. So again, we pick R uniformly at random from 0, 1 for all I, set SI to be all the vertices such that the distance between the terminal and the vertex is at most R. Now we'll initialize x is equal to 0, and then we'll just say for I going from 1 to k, cut basically cut the edges going from SI minus x. So think of x is what has already been, at some point we've already cut all of x out. So there is no need. So we only look at, if SI is here, we only look at the edges going from this shaded region out to the rest of the world, out to everything. So only cut the edges that are going from SI minus x to x complement, and then you just update x equals x union SI. This is going to be our rounding scheme, right? So this is just doing the same rounding as before. It's a little bit more careful because and this is going to be very important for us, that when you've already clustered some part, there's no need to cut more edges in that part. Any questions? Okay. Now we're actually going to come back and we will modify this. But first, now let's look at what is the probability that UV is cut. Right, this is what we need to bound. And we need to relate this to the total variation distance of XU minus XV. I should call this XV here. Right, so it's EI, which is the vector corresponding to SI. It's EI minus XV. Okay, we need to relate it to this. Now here is something that is really useful. What is the probability that SI cuts UV? Or by SI, I mean that the edge is going from SI to SI complement. Suppose you just did the old scheme where you just looked at the SIs, you ignored all of this, and you just cut SI and SI complement. What is the probability that SI cuts UV? You can see this is the absolute value of the distance EI minus XV, say total variation, minus EI minus XU total variation. So what is EI minus? So EI is really simple, right? Remember, EI was just bunch of zeros, 1 and that, and here is some XV. What is the total variation distance between EI and XV? You just think of it as when you subtract these, it's all. Sorry?
1 or 0?
No, the total variation distance depends on what XV is. XV is some distribution. Maybe XV is like 0.25, 0.3, 0.2, and whatever, 0.25, something like this, right? This is some vector. What is the total variation distance going to be?
Sorry, I forgot. What is XV?
XV, so think of it as what the LP is basically producing a vector. Just ignore everything that has happened so far. So so maybe I'll go back. So we said that you can interpret the solution of the LP as a vector where you take 1 minus the distance to each terminal. So you can look at that k-dimensional vector, and that's what that vector XV is. But just think of it as the LP is just outputting some distribution XV. It's just outputting some distribution XV. And total variation is simply looking at the max of XV minus XC, looking at the difference with a max with 0. And so the total variation with any of these is really easy to understand. So suppose these are the two distributions, right? And let's just say it's 4-dimensional. So EI was this. What is the total variation distance between these two things?
0.
Why is it 0? So here are the two distributions.
Oh, no. It's not 0. It would be...
Right? So you're going to basically say, okay, 0 minus 0.25, that's negative. So the max of that is 0. 0 minus 0.3, negative, ignore it. 1 minus 0.2, that's 0.8. 0 minus 0.25, that's negative. So the total variation distance is 0.8.
Oh, it's point.
Is 0.8. If you were to look at the L1 distance, you will get exactly 1.6, which is twice that, because you'll also consider these other things.
The closed form expression would just be SI minus ith, not SI, 1 minus ith xvi.
Exactly.
But there's nothing better than that.
That's it. This is a closed form. That's exactly what it is. Right? So the total variation distance over here is simply 1 minus XVI.
Is that useful?
Sorry?
Is that useful?
You'll see that it's quite useful because this is 1 minus XUI. And so what is this difference now? XVI minus XUI. So this is the probability that SI cuts UV is XVI minus XUI. So what is now using this, this is not going to give a 3/2 approximation. But using this, can you tell me what is the probability that UV is going to be cut? What is the probability that UV is going to be cut? Just by union bound, this is at most the summation of the probability I going from 1 to k, the probability that SI cuts UV.
So that's the total variation distance between XU and XV.
Is it the total variation? You're almost there.
But
Sorry?
it's related to the total variation. I don't know.
Exactly, it's related to the total variation. What is this? What have I written here? What norm is this? Sum of absolute value of differences. What is this? I have two vectors, xu and xv. I look coordinate by coordinate. I take the differences in the absolute value. What norm is this?
One norm?
This is the one norm, exactly. This is the one norm.
But it is twice of the total variation.
Exactly, this is twice the total variation distance. So the probability that UV is cut is twice the total variation distance, where this is our notion of distance of UV, right? So this gives a 2 approximation. This is the 2 approximation here. We need to improve on that. But this gives a 2 approximation. This gives a 2 approximation when I choose the R to be in 0 and 1. I don't need to choose it between 0 and half. Why is that? Because remember, we had this issue before that the problem is an edge can be cut by every SI. And so when you start summing that up, it would become k times the distance. But here, the probability that SI cuts UV only depends on the ith coordinate. And so when you sum these things up, you only get twice the distance. You don't get k times the distance, because these things, essentially, one way to think of this is potentially much smaller than the total variation distance. So you get a sharper bound on the probability that SI cuts UV. Before, we would just upper bound this by the distance. But here, you get something much smaller than the distance. Potentially. So this gives exactly, so this is where, you get the one norm is the probability that it's cut, which is 2 times the total variation distance. Hence, you get 2 times the distance. This gives a 2 approximation. So in other words,
Been the total variation anyway, because then it would be.
I'm sorry?
It would never have been the total variation, because it would just reduce to the IP.
Then you would get an integral solution, exactly. In some sense, if you want to think about that, what happens is, if k is equal to 1, or actually technically
Equal to 2, but
k equal to 2 actually boils down to sort of like k, okay, you're right. So k equals 2, will essentially, one way to think about it, so it essentially like reduces to k equals 1, because what you do is, okay, it's a bit annoying. So technically, you don't have to cut all the SIs, you cut everything but one of them.
Yeah, that's why we had k minus 1.
That's why you have k minus 1. That's why you have k minus 1. But if you work the math out with k equals 2, and you only need to cut one of them, so you say, what is the probability that S1 cuts it? Then you'll get exactly the distance. And this will again show you that that is integral.
But that is also because the ST min cut is basically integral.
Yeah, but this is like, let's just say it's a long-winded alternate proof that ST min cut is integral. Because that would just be the probability that S1 cuts it. So again, if you go through the motions, this gives, again, a 2 times 1 minus 1 over k approximation. Right, so again, because you don't have to cut all of them, you just cut k minus 1 of them, and that's good enough. But this thing here is really important. The probability that UV is cut is basically twice the variation distance, but this is also very important here. The probability that SI cuts it is exactly the difference between the ith coordinate. Okay.
How does the XV is calculated, these real numbers in each dimensions?
Yeah, so how do you calculate the XVs?
Yeah.
So what you do is first solve the LP. Solve this LP. And then set the vector XU to be 1 minus the distance, 1 minus these distances. That's how you get the vector. Does that make sense? So you take the LP solution and you interpret it as as vectors.
But I remember that DSIU equals to 0 or 1, so these would be all 0.
No, that is only in the IP, but in the LP you have a relaxation.
Oh, I see. We gotta do the relaxation first, right?
Well, I mean, you're solving the LP. This is the LP that you're solving. This LP has all these constraints. And you're solving this LP.
Oh, I see. So it doesn't have to constrain that DUV equals 0 or 1.
That would be NP hard.
Yeah.
Right? That would be NP hard. So you solve this using an LP solver. And once you get these distances, you can interpret these distances as these vectors. So you construct these vectors, and then these vectors can now be interpreted as the simplex. And then over there, you can now do all of these calculations. Or technically, you can just generate this set by randomized rounding in this way. Okay, so how are we going to go beyond the 2 approximation yet again? And what we now observe is we observe something a little bit more careful. So I'm going to call these iterations. So I'll say in each iteration, there are 3 possibilities for edge UV. So the first one obviously is that the edge is cut. Now when does this happen? And let's just say that without loss of generality, so let's say in each iteration I, so I'm looking at the ith iteration, without loss of generality, let's just say di of u, which is is less than equal to, well, okay, so we're not using this. So remember we said that the distance is just 1 minus x vu. And this is 1 minus x uv. Right? So these are the distances. But we can just say, without loss of generality, let's just say the distance from SI of u was less than equal to the distance of SI of v. Right? Just relabel u and v so that this is true. So it could be cut. So what does that mean? It means that this r lay in the distance of SI of u, distance SI of v. Okay, so r lay in this region. The second, and this is interesting, is what I'll call captured. So when it's captured, r is actually greater than the distance of SI of v, and it's left if r was less than the distance of SI of u. So here's the cartoon picture, right? So here's S, and here's your edge uv, and your r is like a radius that you're drawing. So if the radius was here, then of course this would be SI, nothing happens to this edge. If the radius is here, then it gets cut. What happens if the radius is here? What happens when the radius is so far out that actually the edge is inside the ball? Look at the algorithm. Question, can the edge be subsequently cut? You're removing everything that's been captured. Sorry, say that again?
I got slightly lost when you repeat the...
Okay, so I'm just saying that there are three possibilities for any edge in the ith iteration. It's either going to be cut, captured, or left, depending on where r lies with respect to these things. Here's the cartoon picture, right? R could be less than du, in between du and dv, or more than dv, where dv means dsi of v. If it is captured, then si contains the entire edge. What we're doing now is then x will then contain si, and in the subsequent iterations, we always do not cut edges within x. Right? We never cut an edge that is inside x. We only look at edges that go outside of x. So my question is, sorry, say that again?
Is that not a problem?
Why is that a problem? You're just being safe, right? Because, so think of it as you're clustering. And so you've removed this cluster. Now let's say from this vertex, the cluster looks like this. Why should you remove these edges? They're already disconnected. All of these vertices are already disconnected from here. So removing these edges is wasteful. You only need to remove these edges. So this becomes x. So what you'll say is, I never cut an edge that has already been captured. It's already been taken care of. You see, the blind thing to do is to simply just remove those subsets just by cutting Si from the rest. But then you could be the clusters could intersect and then they're cutting each other, which is unnecessary because you're already separating them by just removing one of them. Does that make sense? This is a very important point here because this is how we're going to go from 2 to 3 halves. So what happens when an edge is captured? If an edge is captured in an iteration, what can you say? Sorry?
Are you looking for that if it's captured, it's not going to be cut?
Exactly. If it is captured, it cannot be cut in a subsequent iteration. If an edge is captured in iteration I, it cannot be captured in a subsequent iteration. Now we start coming to the heart of our analysis. The probability that UV is cut in the ith iteration means that to be cut in the ith iteration exactly, so is cut exactly in the ith iteration, means that it has to be left in all the previous iterations and then cut in the ith iteration, because if it's captured, then it is never going to be cut. So what this means is this is the probability of the intersection of a collection of events. So the intersection of these events going from j to I minus 1 of uv is left in the jth iteration. Right? So it's the intersection of all of these events, and uv is cut in the ith iteration. This is what needs to happen. Does this make sense?
Yes, got it.
This is equivalent to R lies in this DSIU, DSIV. But these, okay, so now I'm going to introduce some formalism to make this clear. So we fix UV. We're trying to bound this probability. So let's fix UV. Let I of j be the interval min of d sjU d sjV. So just looking at the min and the max, because I don't know which one is, it might change depending on sj u sjv. Okay, let it just be this interval. I guess technically there's one more, right? So you have all of these intervals, ij, I1, I2, right? So I'm just going to sort of draw these here. So this is, maybe this is I5, 3. This is I5. This could be I1. And let's say this is the ith iteration. So what needs to happen? Okay, and I'm also going to sort of, abusing notation, I'm going to go back here and just say that this means R is inside this interval. I'll just say R is greater than the interval, R is less than the interval, just for convenience. Technically, I mean greater than the bigger endpoint, less than the smaller endpoint, or in between, but I'll just use this notation. For this to happen, for this event, which is UV is left in the jth iterations. So this is basically, it's equal to the probability of all of these events that R is greater than these intervals and R lies in the ith interval. Right? So, for example, in this picture, if R lies here, then it is greater than all of these intervals. And it would lie in here. But suppose
The I1 and I3 can be related like that. There is no issue with that.
sorry, they can be?
Like, can I1 and I3 be related like this? It's
You have no idea how, because these are all different sources, right? Think of it as these are different points on the k-dimensional simplex, right? And this is some edge that lies in here. So you don't know, I1 is with respect to this, and I2 is with respect to this, and I3 is with respect to this, and you don't know how this is oriented. So the intervals could be behaving in any which way. So do you see that the ordering of the intervals is relevant? Like if if capital I of small I was here, then the game would be very different, because as soon as I1 is processed, if R lies to the right of it, then immediately it cannot be in this interval. And you're already done. The edge has already been captured. Right? So
that's why I'm asking, what does it mean for, like, can I3 be like less than loosely I1 for R to be captured in the IN?
good. So you see that it implies certain constraints amongst these intervals. For this to happen, certain constraints need to happen. Right? That's my point, right? So it depends on how these intervals are set up. It could be the case that this could never happen, right? In this case, because if R is greater than I1, then it can never be inside this interval. But if they were this way, then it could happen. And the algorithm has no idea, because all of these, it doesn't even know how to process these intervals, and it has to do all of these in some consistent way with R, and maybe for different edges things could be different. So this is where the natural idea that comes up in all of this is process the terminals in random order, or technically uniform random order. Because your hope is, if this is a low probability event, if this becomes a low probability event, then you're in good shape, because that means the edge will not be cut. It'll end up being captured with high probability. So we're going to go back to does this make sense? Does this picture make sense? Questions? Okay. We're going to adapt this algorithm by picking R and picking, well, I should say this here, sigma is a uniform at random permutation over the terminals. And instead of looking at in the ith iteration, we look at sigma I. In the ith iteration, we look at sigma I. Sorry, this is a bit messy. Does this make sense? So we're basically just permuting the vertices at random in the hope that it might get captured with high probability. Because if you don't permute, there could be some pathological ordering where maybe the vertex always gets cut. But by randomly ordering, we're trying to boost our chances that an edge might get captured. Does this make sense? Questions, please. Or a thumbs up if this is making sense, if this algorithm makes sense now. Okay. So now.
Sorry, I
yes.
have a question.
Yes.
So if R belongs to a uniform distribution, so why there would be a parameter? I think uniform distribution are all the same, right?
That's right. R is which parameter?
Do you think sigma is our parameters?
No, it's a permutation.
Oh, sorry.
No, so R is the threshold, but I'm just instead of processing the vertex, instead of processing the sources going from 1 to k, I'm just going to randomly permute the sources according to sigma.
Oh, I see. So sigma is a permutation of 1 to k, right?
Yeah, exactly, of the sources.
Okay, so that's the parameters. I got it. Okay.
Yeah.
So you gotta choose different segments to iterate through 1 to k.
You're just going to process this. Previously, you were processing the sources in order. You were going from script S1, script S2, script S3, so on and so forth.
Yeah.
Now I'm just going to do it in random order.
Okay, yeah, I got it.
So now we can look at this, and instead of it being, it's sigma of this. So what is the probability that this happens over R and over sigma? And this is the key. This is the key. Okay, so now let me, I want to do this calculation a little carefully. So I'm going to go back. Okay, so here is the picture that we have, and this is the probability that it is cut in the ith iteration. But another way of looking at this is to say, so we have all these intervals here, right? And these intervals, I5, I10. Remember, all these intervals are defined with respect to UV. Right? This is just min of DSJU, so on and so forth. So I3, I19. And maybe
I have a question.
Yes.
So, is it obvious that the union of the intervals is a cover?
Is a cover of what?
Like some neighborhood of R at least?
No, not necessarily. The union of intervals, no. All you know is that the sum of these lengths, so one thing that you do know is that the sum of these lengths, this is basically like 2 times, this is the L1 distance. Right? Because this is just the difference in coordinates. But R is being chosen from here. Okay. So now we can ask, instead of asking this question of what is it the probability of cutting in the ith iteration, let me ask a different question. What is the probability that UV is cut by the ith interval? What is the probability that UV is cut? So you can fix an interval. So fix, let's say this is II. So what is the probability that UV is cut by this interval? Now to do this analysis, I'm going to say IL is the interval with smallest left endpoint. So that is this interval here. So let me refer to this as IL. This is the one with the smallest left endpoint. I'll say, what is the probability that UV is cut by this and not IL? And then I can look at what is the probability that UV is cut by IL. So what is the probability that UV is cut by IL? This is at most the size of IL, which is exactly XUVL minus XUVL, right? This is just saying that, look, let me look at the smallest interval. And this is the probability that it is cut in this interval. Now, what is the probability that it is cut by II and not IL? What needs to happen? So here is II, here is IL. To be cut by this interval, who needs to be processed first?
IL, because whatever is captured by IL is no longer going to be cut.
Or the other way around, II has to be processed first, because if IL was processed first and R lay in here, then it's already captured. Right? So for UV to be cut by II, R has to lie in here. But if IL was processed first, so if L was processed first, then it would already capture. Does that make sense? So the probability that UV is cut by IL is basically, so this is where we use the fact that the random permutation is randomly going to, give me a second. The random permutation, so this is again the probability over sigma and R. So this is the probability over sigma and R, or this is at most the probability that IL appears, or I should say L appears, This is at most the probability over sigma and R that L appears after I in sigma, in the permutation, and R lies in I. But these are independent events because the first one depends only on sigma, the second one only depends on R. So the probability that it is cut, and what is this probability? What is the probability that L appears after I in sigma, when L and I are just they're just two terminals? What is that probability? Now you're randomly permuting. What is the probability that L appears after I?
1/2.
It's a half, exactly. So this is equal to a half times the probability that R appears, R is in II, and this is simply the length of II divided by 2. So this half that we get over here is going to help us now. So so now let me sort of do it all. What is the probability that UV is cut? Right? And I say, basically I can just do union bound. I say this is the probability over sigma R that UV is cut by IL plus the summation over all I not equal to L of the probability sigma R UV is cut by II and not IL. Right? And now I basically plug everything in and I'm going to get the bound that I want. Okay? So how am I going to do this? So I said this, and I'm actually going to do a fairly weak bound. The first probability was just IL, plus the second probability was a summation over I not equal to L of this interval I. Now remember that the summation of the size of all the intervals, this was at most the one norm. This was at most the one norm. So I'm just going to bound this as follows. I'm just going to say this is half of the summation of I going from 1 to k. So just everybody of II plus half of this. Right? What is this quantity? This is exactly half of the one norm, which is the total variation distance. This is total variation. What about this? I can actually bound any one of them by the total variation distance. Remember, this is what I said over here. If I look at any one of these, xuvi minus xvi, that is at most the total variation distance. Right? Because I can look at any one coordinate and take the difference, and this is at most the total variation distance. So this is also at most the total variation distance. And so this leads to a bound of 3/2 of the distance basically between u and v. So the probability that uv is cut is at most 3/2 of the distance. Right? And so this becomes our lemma right here, is that the probability over sigma and r, so there is this randomness amongst all the terminals, is at most 3/2 of the distance. And then if you sum this up, so I'll just complete the proof, is that is a theorem, is that this scheme gives a 3/2 times 1 minus 1 over k approximation. And the proof is saying that, okay, so the expected number of edges cut is equal to, by linearity of expectation, is the sum over all uv and e, the probability of sigma and r, the probability that uv is cut, which is at most uv and e of 3/2 times the distance of expected cost of edges cut is this times c uv times cuv is equal to 3/2 times the cost of the LP solution. Right? And this gives a 3/2 approximation, and we can, choose the best, or I should say the smallest k minus 1 amongst the k cuts to get 3/2 1 minus 1 over k prox. Okay, so that completes the proof. Any questions?
So I have a question. So what's the point that we calculated this probability? Is that used for calculating the time complexity?
No, it's for the expected cost of the edges cut. This is actually I need to be a little careful here. I've fudged something here, so it's actually it should be. Let me just say it's a 3/2 approximation, because you can't get this. So it's just a 3/2, and I think that from this you get like 3/2 minus 1/k. But sorry, I need to go and check this, because if you did that, then you'd get a 1 approximation for k equals 3, which is not possible. Anyway, sorry. So the point of this scheme is to show what is the probability that an edge is cut by the scheme, which is to bound the cost of the rounding. So remember that in all our rounding schemes, we have this alpha. This is the cost of the rounding. Like we do this rounding of alpha and we say, okay, how much is alpha going to be? Like we did this for vertex cover, we did this for set cover. And then what we're now doing is we're saying, what is the cost of rounding? Because the rounding scheme is basically doing this cut, right? This is what the rounding scheme is doing. And it's trying to determine how many edges are cut. So we're saying, what is the probability every edge is cut? And we use that to bound the expected cost.
Oh, I see.
So I think it's 3. I have to be careful here. So I need to check this. So I don't think this is totally correct, but we get a 3/2 approximation from this calculation.
What happens if we can prove that this is the best possible?
If this is the best possible? Actually, this is not the best possible. That is known. So the story is quite complicated. For k equals 3, we can get a 12/11 approximation with a matching integrality gap. And this is by Cunningham and Tang in 99 and Karger in 04. For k greater than equals to 4, the story is pretty complicated. It's not yet resolved, and I've dug out some fairly recent papers that have been talked about this. You can get something like a 1.29 approximation, and this is by Sharma and Vondrak in 2014. The integrality gap of the Ckr relaxation is also an open problem. So the integrality gap it's known that it's at least 1.2, and actually this was Angelidakis, Makarichev, and Manurangsi in 2017, and this is improving upon, like, someone then improved this to 1.0, like actually something like that, using an extremely complex construction. And this is, yeah, it was essentially like this really long-winded thing where they, and Berchi et al. And this is fairly recent. Like this paper that I saw was 2018. But these are, very sophisticated constructions. So this is what is known with to the best of my searching. I mean, I'm not my information might be dated. So, but this was 2018, and this is what I saw from there. So, but it takes a fair bit of effort to improve on the 3/2 approximation, and 3/2 was a pretty big deal. So the Ckr relaxation gave that. One thing that I was, I thought I would get to, but I did not, is, and I'll mention this sort of just in the last 5 minutes, that, there's this problem, multi-cut, which is now instead of multi-way cut, you're given k pairs, not k vertices. S1, T1, SK, TK. And so we cut edges to just separate the SI-TI pairs. Right? So you just need to separate the pairs from each other, not all terminals from each other. It turns out that you basically use exactly the same relaxation, except replace this with SI and TI. Like replace it with SI, TI, and you don't even need these other things. You just make it SI, TI without these other constraints, without these other conditions. And if you apply the same rounding scheme, so you apply the same rounding scheme here with a similar analysis to what we did, but it's different because we're doing multi-cut. But you can essentially apply the same rounding scheme. Then, this is proven by Ckr, but in a different paper, is that this gives an O log K approximation. And this, I believe, this is probably also like 2000. There was also a paper by Garg, Vazirani, and Yanakakis in 99, who also gave a log K approximation, but you can get a log K approximation, sort of same approach. I should say similar probably as what we did, without the extra distance conditions. Without the extra distance conditions. And you can basically do a very similar analysis, but instead of you basically get like the harmonic, you'll get the harmonic number. Again, you have to look at sigma, look at the permutations, you have these intervals and you have to consider the order amongst them. But essentially it breaks down into a calculation that is very similar. You don't have this L1 and total variation anymore. So it's actually simpler. It's actually simpler to do this analysis. And you get a log K approximation from that, which again was a fairly important result. There was a breakthrough result of Arora Rao Vazirani techniques from which were used to get square root log K, log K. But this is another very important problem, multi-cut. So multi-cut and multi-way cut are sort of important generalizations of min-cut, which have seen lots of very exciting research and techniques over the past 2 decades. But hopefully, this gives you a flavor of some of the techniques that are used, and this is getting closer to sort of what I'd say is modern combinatorial algorithms, the kind of methods that people use now in research. So I'll end here and I'll take any questions that you have.